the lunar surface activities on this mission are considerably expanded over those of the first lunar landing mission. Crew will spend about 31.5 hours on the surface, some 10 hours longer than the Apollo 11 crew, which permits 2 periods of extravehicular activity, each of 3 hours and 30 minutes. Now, this in turn permits us to take a more ambitious approach to the scientific activities we've scheduled for the crew. So briefly, I'd like to initially discuss the major events that will occur on the surface, to include the post-landing checkout, the 2 EVA periods, a 9-hour rest period, several eat periods, and then the preparation for ascent. Now, immediately after landing, the flight crew and the flight controllers on the ground will enter into the post-landing checkout phase, whose objective is to assess the LEM capability to either remain on the lunar surface or initiate an early ascent. Now, the first such decision is timed so as to permit a liftoff at the PDI plus 16 1/3 minutes. That's 16 1/3 minutes after initiation of the powered descent, which will be some 3 to 5 minutes after landing, depending upon the amount of time spent in the hover mode during the landing approach. The second stay-no-stay decision is based on a little more extensive evaluation of the LEM systems, and is scheduled to cause liftoff to occur at PDI plus 21.5 minutes, or about 10 minutes after the landing. And then the final succeeding decision point after this will permit a liftoff at about 115 minutes after the landing event, which is after the completion of the first revolution by the command module. Now, assume that the post-landing checks do not require deviation from our normal timeline, while the crew will proceed with the partial power down of the lunar module. They'll take photographs of the surface through the lunar module windows and report to the ground on the landmarks that they saw both during the final stages of the powered descent and which they currently see out the window. This, of course, to help determine their accurate location. Following a 1-hour eat period, then they'll prepare for the first EVA period, which is scheduled to begin at 114 hours and 40 minutes ground elapsed time. Now, the principal events of this EVA are the contingency sample collection, the deployment of the erectable S-band antenna, a TV from the surface, deployment of the various experiments, and collection of the so-called selected sample. The commander initiates the EVA much as he did in Apollo 11, coming through the hatch feet first on his hands and knees. And this will occur at about 0600 a.m. Eastern Standard Time on the morning of 19 November. As he initiates his descent down the ladder, he'll pull a D-ring, again as on Apollo 11, which will deploy the Modular Equipment Storage Assembly, or MESA as we call it, and this in turn will initiate the TV sequence. We still have some hopes that this will be in color. He'll then continue his descent to the footpad. He'll evaluate his ability to ascend the ladder, and as you all recall, it's a long first step. He'll then step off onto the lunar surface about 7 minutes after the initial egress. Meanwhile, the lunar module pilot has been photographing his progress down the ladder. Now, after a brief evaluation of his stability and mobility, he'll collect a contingency sample similar to Apollo 11 and hang this sample from the ladder. Then, while the lunar module pilot is making his final egress checks, the commander will erect the MESA table, and he'll put the portable life support system spare batteries and the lithium hydroxide canisters and the contingency sample into a equipment transfer bag, connect this to the lunar LEM equipment conveyor, and they'll transfer the bag up into the command module. The 2 crewmen, after they pass this bag up, the LEM pilot will then remove the contents and replace them with the 70mm Hasselblad cameras containing color film. And the bag is then transferred back to the surface, where the commander will remove his camera and then photograph the LEM pilot's egress and descent. Now, as the LEM pilot evaluates his mobility on the surface, the commander will initiate deployment of the S-band erectable antenna. He completes this deployment during the next 17 minutes while the lunar module pilot unstows the TV and will deploy it at this location in order to record the events that are taking place in the vicinity of the limb and around the mesa. We also plan at this time to deploy the American flag. It will be about this point, although these plans are not yet firm. There will be a flag similar to the one deployed on Apollo 11. The limb pilot will then deploy the solar wind composition experiment, which consists of a 4-foot square sheet of aluminum foil suspended from a pole. This is quite similar to the one on Apollo 11. The big difference from Apollo 11 is that it will be collected at the end of the second EVA period, which will permit it to be exposed for some 30 hours. The limb pilot will then move the TV around to the 8 o'clock position, which is to the left rear of the lunar module, to permit observation of activities which will shortly be occurring there. The two pilots will then move counterclockwise around the limb, taking panoramic photos, observing the limb for problems, and taking photographs of the limb footpads. Now, the next 1 hour and 15 minutes will be devoted to deploying the Apollo Lunar Surface Experiments Package, or ALSEP. Now, the ALSEP is designed to provide us information first, which will let us understand something of the makeup of the interior of the moon. Second, to develop some understanding of the surface composition and near-surface composition of the moon, and those things which make this composition change. Next, we hope to get a better understanding of the origin of the moon and the events that have occurred to bring it to its present configuration. And finally, to obtain engineering and scientific data which will be used to base future mission decisions. Now, the ALSEP, as shown on the right, consists of a central station and a power supply and a varying list of scientific instruments. ALSEP 1, which will be flown on this experiment, contains the 5 instruments shown here: a passive seismic experiment, a lunar surface magnetometer, a solar wind spectrometer, a superthermal ion detector, a cold cathode ion gauge, and we'll go into each of these as they're deployed. Now, the limb pilot, on arriving at Quad 2, around to the left rear of the limb, will open the SEQ bay door, and the two crewmen will remove the ALSEP packages and lower them to the surface. The limb pilot then will rotate down the cask that you see there, which contains the radioisotope capsule for the generator. He'll remove the cover from the cask, extract the capsule, insert it into the power generator. The crewman will prepare the 2 packages for transfer by connecting them with a carrying bar. The commander will then carry the sub-pallet containing the superthermal ion detector experiment and the television out toward the deployment site. He'll emplace the television about 90 feet from the limb, which is the extent of its cable, and then he'll proceed with the lunar module pilot, who will be carrying these 2 packages suspended from the carrying bar out to the site, located at a minimum of 300 feet from the lunar module. Now, of course, they'll stop to rest periodically en route. Now, once at the site, their initial actions are to perform a brief survey to determine the exact locations for deploying each of the experiments, and then they'll separate the experiments. Now, the commander initially deploys the solar wind spectrometer about 13 feet from the central station. Now, this experiment is designed to measure the energies, the densities, incidence angles, and temperature variations of the electron and proton components of the solar wind plasma, which streams to the lunar surface from the moon, or from the sun. Analysis of this data, coupled with that from the solar wind composition experiment, will give us some better evidence of the exact composition of the sun. Now, during the same time, the lunar module pilot will set up the radioisotope thermoelectric generator from package number 2. We'll then place the passive seismic experiment about 10 feet from the central station. Now, this experiment is quite similar to the one that we deployed on Apollo 11, with the exception that the electronic data processing and transmission equipment has been transferred to the central station, which permits us to place this instrument on a stool and give it better contact with the ground. And the skirt shown around the instrument here will provide somewhat better thermal isolation. You'll recall on Apollo 11 we had some thermal problems with the passive seismic experiment. The LEM pilot will then deploy the lunar surface magnetometer, shown here, about 50 feet from the central station. Now, the purpose of this experiment is to measure the variations in magnitude and direction with time of the lunar surface equatorial magnetic field. The data will also be used to derive a better understanding of the electrical properties of the deep interior of the moon and of the interplanetary magnetic field which engulfs the moon. The LEM pilot will then deploy the superthermal ion detector, and really a better name for that is the lunar ionosphere detector, about 55 feet from the central station. This experiment will measure the flux, the number density, the velocity, and the energy per unit charge of the positive ions in the vicinity of the lunar surface. He then carries the cold cathode ion gauge, and a better name for that is the lunar atmosphere detector, to the vicinity of the superthermal ion detector, and in place it's designed to measure the density and temperature, if any, of the lunar atmosphere, which will in turn contribute toward a better understanding of the early history of the moon. Now, during the time that the LEM pilot is performing these events, the commander will have assembled the central station. He will have emplaced the antenna, which you see at the top, and aimed it toward the Earth, and connected up the power generator. The central station receives data from each of the experiments, encodes it, and transmits it back to the Earth tracking station. It also receives commands from the Earth tracking station, and processes these to permit the experimenters on the surface to control the functions performed by the ALSEP instruments. Now, the radioisotope thermoelectric generator, commonly called a SNAP-27, produces about 63 watts of electrical energy. It's used, of course, to supply power for both the experiments and the central station. And it's fueled with plutonium-238 and puts out a heat load of about 1,480 watts. Now, when all is in readiness after the deployment, the commander will apply power to the central station and request the ground controllers to command the transmitter on the central station on. Upon verifying that data is being received by the Earth, and after making detailed photographic documentation of the ALSEP site, the two astronauts will walk back towards the LEM, en route collecting interesting samples as a part of the selected sample process. The samples they collect during the selected sample will be placed in side or way bags, which are connected to the side of the astronauts' pressure suits. In addition, they'll pick the TV up and carry it back to the original position so that it can observe the mesa area and the ladder. Upon arrival back at the LEM pilot will assemble a core tube and take a core sample in the vicinity of the LEM, and then store this in the #1 sample return container. The astronauts then each remove the other's weigh bag, and these are placed on a scale. They'll continue their selected sampling in the vicinity of the LEM until they reach about 34 pounds, or a volume limit, in the bags. Then as the commander seals and packs the bags in the sample return container, the LEM pilot will ascend the ladder, enter the cabin, and apply power to the erectable S-band antenna. They'll then have a communications check in order to check the status of this antenna prior to the commander's ingress. The commander will then place the rock box into the equipment transfer bag, and the two pilots will transfer it up and store it in the LEM. He'll then ascend the ladder and enter the LEM. The hatch will be closed and the cabin repressurized. When this occurs, the two astronauts will doff their portable life support units, and after an eat period, they'll measure the consumables remaining in the portable life support system, principally water, and then initiate the PLIS oxygen recharge. They'll then provide us with an initial debriefing on the events of the first EVA. Now, upon awakening, the crew will have a 1-hour eat period and then initiate preparations for the second EVA. The principal purpose of this EVA period is to perform the lunar geological experiment. Should the landing be performed in the proximity of a Surveyor 3, and I say this is a big if, the sampling will be performed en route to the Surveyor, and then documented sampling and selected parts will be removed from the Surveyor. Now, the lunar geology experiment includes documented samples, core samples, gas analysis samples, and an environmental sample. After depressurizing the limb and opening the hatch, the commander will egress and descend to the surface as before. This is scheduled to occur at about 20 minutes before 1 a.m. on the 20th of November. That's Eastern Standard Time. The lunar module pilot will install the 70mm Hasselblad cameras, now containing black and white film, into the equipment transfer bag, and these will be lowered to the surface. After turning on the sequence camera, he will then egress and descend to the surface. The commander will stow equipment such as the tongs, the scoop, the extension handle, and the hammer into the hand tool carrier as shown here, and retrieve and open the second sample return container. The limb pilot will don a side bag taken from this container and collect the core tubes and sample bag dispensers, and then they will initiate the geology traverse. Now each of the two astronauts will carry a 70mm camera, with the commander also carrying the tongs and the gnomon, which is a little tripod with a plumb bob-like device to indicate the local vertical, and a small scoop, while the lunar module pilot will carry this Apollo lunar hand tool carrier. And during the sampling period, the astronauts will document to varying degrees each of the samples collected. Typically, to initiate a sample, a documented sample, the commander will emplace the gnomon up sun from the sampling site. He'll take photographs of the site then from cross sun. Now, the first such sample, he'll use a polarizing filter to permit some determination of the lunar surface reflectivity. However, after the first sampling, he'll discard this filter. At the same time, the lunar module pilot will be taking photographs of the sampling site down sun. Then after the commander has picked the sample up and placed it in a small sample bag held by the lunar module pilot will place the bagged sample in the large bag here on the hand tool carrier. Now, typical core tube sample will again be started by the commander placing the gnomon up sun of the area to be sampled and taking photographs cross sun. The lunar module pilot will photograph the area down sun. He'll then assemble the coring device, drive it into the ground, step back and take some more pictures down sun, then extract the core device, remove the handle, cap the core, and store the core in this bag on the hand tool carrier. Now, on one such sampling, an aseptic sample will be taken. This will be performed by scooping out a trench some 6 to 8 inches deep and then taking a core sample from the bottom of the trench. At the same time, we'll collect an environmental sample from the bottom of this trench. Gas analysis sample is simply taken by exposing an empty container to the atmosphere for some long period of time and then sealing it up prior to ingress. Now, if the landing navigation was such as to permit visiting the surveyor, and again I'd like to emphasize that this is a secondary objective, the documented sampling will be performed en route and then will be interrupted at the surveyor site. Now, we have some concern about our ability to maintain communications with the crew, since the surveyor is located some 25 to 35 feet below the level of the surrounding surface. All communications from the Earth are relayed to the two astronauts through the lunar module. However, the lunar module pilot can receive directly from the limb, but he has to transmit to the commander and have this relayed through the plis on the back. So this happens automatically, but he cannot communicate directly with the limb. Now, upon arriving at the surveyor site, the limb pilot will enter the crater first to evaluate the ability of both pilots to negotiate the 14 to 15 degree slope both up and down, and he'll be connected to the commander by a 30-foot tether. Should this evaluation prove successful, both pilots will then enter the crater while the ground controllers monitor the communications problem. Mission rules dictate that the pilots cannot be out of voice communication with the Earth for more than 5 minutes. So should a communication problem arise, the commander will then back out of the surveyor crater until such time as the relay function can be performed, until he reaches such an altitude that the relay function can be performed. Now, if this happens, the lunar module pilot will continue on down and perform only the photographing investigation of the surveyor. The initial activities at the site require the lunar module pilot to carefully document with color film. He's changed his pack now from black and white to color. The surveyor itself and the area around the surveyor, paying particular attention to the area that was covered by the surveyor TV camera and the several trenches that were scooped into the surface by the surveyor scoop. Of course, these photographs will provide scientists with some interesting data on surface erosion in the known period of time which has elapsed since the surveyor transmitted its TV pictures back to Earth. And while the lunar module pilot is busily involved in performing this detailed photography, the commander will be reading each item off of his checklist. When the photography is completed, and should the communications permit both pilots to operate in the surveyor area, the LIM pilot will remove a large cutting tool which is stored in a parts bag on the back of the commander's pliss. He'll hand these cutting tools to the commander, and the commander will cut two of the the first thing he'll do is cut this cable right here, which is a power cable, up to the surveyor TV. And the bacterial load which was on this cable at launch was well known, so that its return will provide interesting data on the effects of the lunar environment in some 2.5 years. The sample will be caught, not touched, be caught in an environmental container by the lunar module pilot. He'll then proceed to cut two of the 5 supports, and this is which hold up the surveyor TV camera. These supports are a little bit difficult to see, but they're right down in this area. They'll then proceed around to this area right here. They'll cut a 2-inch length of that aluminum tube. It's an unpainted aluminum tube, and this will be placed in the parts bag to be returned. They'll proceed around. They'll collect glass samples from the top of compartment A here and B, which is around to the back and out of sight. They feel that the glass mirror, which is on the top of these compartments, is now debonded and should be readily picked up. They proceed back around the far side of the surveyor, again back to the TV, cut the remaining 3 supporting tubes, remove the camera, and place it in the part sack on the back of the commander's pliss. They'll then discard the cutting tool, return to the crater rim, pick up the hand tool carrier, and proceed back towards the limb along a different route, continuing their documented sampling. Now, upon arrival back at the limb, the commander will retrieve the solar wind composition experiment, which we placed out at the beginning of the first EVA, and store it along with the various documented samples in the number 2 sample return container. The lunar module pilot will obtain photographs with the Apollo lunar surface close-up camera, a 35mm self-illuminating stereo camera, similar to the one flown on Apollo 11. Upon completion of these activities, he'll ascend the ladder to the limb porch and enter the cabin. The commander will place the sample return container in the equipment transfer bag and transfer first it and then the surveyor parts bag up into the limb. The commander will then ascend the ladder and enter the limb. Now, after the hatch is closed and the cabin is repressurized, the crew will transfer to the limb environmental control system. They'll doff their portable life support systems, depressurize, reopen the hatch, jettison their plisses and other expended equipment onto the lunar surface as we did in Apollo 11. Now, planning has been done to extend either or both of the periods of extravehicular activity up to an extra 30 minutes each, based upon a real-time evaluation of the expendable consumption. Should this occur, the additional time will be taken out of the sleep period shown in the middle between the two EVAs. Now, if the first EVA is extended, of course, the first thing they'll do is to complete any unfinished tasks, or if they have none, they'll go ahead and initiate the documented sampling on the first EVA. If the second EVA is extended, again, they'll complete any uncompleted tasks and then utilize the extra time for additional sampling. Now, after completing their post-EVA checks, the crew will have a short EVA debriefing to the ground. They'll have an eat period and then begin 2 hour and 30-minute launch preparation sequence. Liftoff is scheduled to occur at 142 hours ground elapsed time, or about 9:22 a.m. Eastern Standard Time on the 20th of November. During the time that the LEM has been on the surface, the command module pilot, of course, has been in orbit above them, performing his normal housekeeping chores and navigation activities. Early during the first EVA, he'll perform a plane change to ensure that the orbit of the command module passes over the landing site at the time of lunar module liftoff. And this maneuver is required because the orbit inclination is 15 degrees, which allows the moon and, of course, the landing site to rotate underneath it. Late during the second EVA, he'll perform the S-158 experiment, which consists of photographing the moon with a ganged array of 4 Hasselblad cameras with a blue, red, infrared, and green filter to permit multispectral analysis of the lunar surface. This is quite similar to the SO-65 experiment which we performed on the Earth during Apollo 9. I'd now like to turn it back over to Captain Lee, who will get us off the lunar surface and back home.
After about 2.5 hours of preparation, the ascent event should be quite similar to what we had on Apollo 11. Liftoff we'll attain approximately 50 feet per second in about 10 seconds and at about 240 feet altitude before he starts pitching over into the insertion into the orbit, lunar orbit. One change we will have on this ascent performance is that soon after liftoff, they will yaw 20 degrees to make sure that we have good solid communications with the ground. This burn, as noted here, will be approximately 7 minutes and 10 seconds, and your various events are shown here, which I've already gone through for the co-elliptic sequence initiation, of plane change, the CDH, TPI, and final docking. So I won't go through those. If you have any questions, we can refer to them later. As I mentioned earlier, our plan on this mission is to impact the ascent stage to clear orbital debris, and this shows essentially how we plan to do it. We will jettison in a radial position at this GET, 148 hours approximately. The separation will be a 1 foot per second retrograde maneuver. The two will come around. At this point, the RCS engines on the ascent stage will perform a retrograde maneuver of about 180 feet per second to bring the ascent stage into an impact targeted approximately 5 miles to the south of the landing area. I would like to point out that normally we should have about 300 feet per second capability left if things have gone normally up to this time. Next slide. I mentioned also that the extra day in orbit, lunar orbit, was to pick up some bootstrap photography, and this is to give you an idea of the 3 sites, Descartes, Lalande, and Framar, that we're very interested in getting photographs of, and these show you essentially their location and the revs we hope to pick up this information on. I would like to also emphasize that these are primary. We will also try to get some other photography of the areas during these orbits, additional orbits around the lunar surface. And we come back to the re-entry phase. I won't spend too much time on this. You've all seen this. Our re-entry is essentially how we have planned it in the past. In this case, instead of 1,285 miles downrange, after re-entry, we're targeting for 1,250 miles. The bandwidths here are primarily to indicate the difference times in the launch window.